Hi, welcome to another video for Applied Math. Now, this video is really a continuation of what I did in class yesterday. I talked about a couple different ways that you could go about finding two linearly independent solutions. And in particular, the thing that I started on the board and didn't quite finish was that you could solve an equation for a power series solution, and you could just use a couple of different kinds of initial conditions. And once you get both of those different initial value problems solved, then you've got yourself two linearly independent solutions to that original equation. So I'm going to finish that up now. So let's get started. Here we see a copy of my notes from Friday's class. I talked about how to find two linearly independent solutions to our second order differential equation in standard form. And we said, if we solve two initial value problems, one with each sets of these initial conditions, that'll get it for us. And last time in class, we got started on this one. And so that means let's start with a pretty simple example, actually. So this is a constant coefficient problem. We could solve it easier, different ways, but let's find out how it goes when we're trying to do these particular kinds of initial conditions. So when we went through this in class, we assumed a power series solution, and we got ourselves actually one recurrence relation, as you see here, and I just rewrote it and put it in a box so it's a little easier to see on these notes. And now recall that your initial conditions up here form for you your A0 and your A1. And we've addressed this in class a couple of times. So there you are. Here's your A0, here's your A1. Let's plug and chug through that recurrence relation. And I did this one in class. So we got to the point where we had, oh, look, x e to the x is a solution of this initial value problem. Let's call that an IVP instead. Okay, so that's one of them. And I want to go back and do the other one now. So here is exactly the same, exactly the same differential equation with now initial conditions which say, all right, A0 is 1 and A1 is 0. And now I've written down the recurrence relation again. It's going to be exactly the same as before because we're solving the same differential equation. So now what we really just have to do is start with this A0 and this A1 and figure out the patterns. Now these patterns are a little bit tricky, so that's why I kind of wanted to talk through it with you. Won't take too long, but you do have to write out a lot of steps, and I'll try to highlight the places where it's a little tricky. Okay, A0 and A1, I know what they are. Now let's start working through all of the rest of the recurrence relation information. So if I need to get A2, A2 will then be in terms of A1 and A0, and there's what you see. And you just got to plug and chug through some of these. So let me write a few of them here so that you can see. And I've tried to highlight what the M value is for each, so it's easier to actually eyeball this in the end. So A3 is a minus 2/3. A4, you know, there's a couple different ways to write it, and here's the secret. Even though a minus 1/8 might be what you think you want to write, resist the urge and leave it in this factorial form. I know it's odd, but it's sometimes illuminating to do that, and it will be in this case. Now A5, here we go, is minus 4 over 5 factorial. A6 is minus 5 over 6 factorial. hopefully you can start to see the pattern here. I wrote one more down before I actually said, okay, I see the pattern now. AM is simply a negative m minus 1 divided by m factorial. That's the hard part. You're just going to have to try to work on this and eyeball it. You got to stare at it a long time, and I can't help you with that. Mostly that's up to you. But once you get here, let's go put it all together. All right, because that's the important piece, that once you get this done, let's go and see what we see happening down here. So return to your original power series expansion. I'm going to plug in my A sub m, and notice that that A sub m actually works even for A0 and A1 in this case. So you're just going to have to go back and check that. Plug and chug through those numbers as well. If I plug in what my AM is, then I have this expression right here. And now that's y of x. Well, I can see how maybe this is a place where I want to split things up, because if I could split this into two pieces like you see here, then I can start to recognize some things, right? So this, I recognize that. That is nothing but an e to the x in series form. And now I have to play a little bit more with the algebra here. I get an m over m factorial. Well, factor or expand that factorial and recognize that those m's cancel. And this, oh, sorry. This 1 over m minus 1 factorial that you see here, well, I can actually just adjust indices on this a little bit, right? I've got an x to the m minus 1. All I really need to do is play a little bit more. So now I need to shift m up by 1. And when I do that, then I shift my index here down to 0 because I go down by 1. And then I can recognize, oh, well, actually, if I factor out, and this is a little hard to see, but if you actually factor out an x and do that shift, you can get yourself to an x e to the x term. So there's a little bit of work to do there, but it's just some algebra. I think you can handle it, and you get to the place where here is your second linearly independent solution. So now, by solving these two separate initial condition problems, what I have generated for myself is an IVP1, if you like, which gives me y1 of x equals x e to the x. And then, and now what I get for the second one is a y2 of x, which is actually e to the x minus x e to the x. So these are not our standard ones, but they still work. They're still two linearly independent solutions. Take a look at that and just kind of digest what's going on there. So before, when we dealt with constant coefficient ODE second order equations, we just did our characteristic equation. You can actually do this with series as well. Sometimes you're not going to come up with sort of the standard ones that we would come up with the characteristic equation. And if you go back through and actually look at that constant coefficient equation, I think you'll find that you've got a repeated root problem, and you can come up with your standard two linearly independent solutions, and then you could generate this y1 and y2 that we got with our power series. So you might come up with a little different form than what you would get with kind of standard methods, but hopefully this kind of gives you the idea that you can get those linearly independent solutions by carefully specifying your initial conditions in such a way that you're guaranteed linearly independent solutions. All right, thanks for watching. You guys have a good week, and I will see you in class. Thanks. Bye.